Hello and welcome to Bungalows for Bachelors. We are going to talk about how things fail. There's pretty much two ways the items and the structural elements we're talking about are going to fail. The first way is through stress or like structural failure where something breaks or bends too much and fails by buckling. And the second way things fail or fail to meet our criteria are by deflection, which is more related to, well, things are going to be too bendy, things are going to be too curvy. It's not going to look good. The whole point of building houses is we want to build them square, plumb, and true. And if I have a big old beam in there in my house and it's just too bendy, it's deflecting down under the weight. It may not break, but it's kind of looks bad. So there's two limits that we designed to, and we want to keep in mind both of them. So I'm going to talk first a little bit about stress, see if I can break this down. I'm not going to get too crazy into engineering principles because we don't really need it. We just need to know how to apply things. But I'm going to talk a little bit about it. So the first thing we need to know is if I have a simple span beam, it's sitting on a wall on both ends, and I have, let's say, a stud wall or some even load across this thing. Let's say each one of these things represents a stud sitting on it. So we have some uniformly distributed load, something's the same weight across the whole top of the beam. Basically what we know, let's say there's 6 arrows here. Well, we know that let's say each arrow was worth one unit of something. Then we know that the arrows in this location that are going to hold up this beam are, we're going to need 3 arrows here, three lengths worth of arrows here, and 3 on this side as well. Because there's 6 on the top, and the weight's got to be supported by something. So basically what that means is the wall's going to, for this beam to not be moving, which, you don't want it to move. You put the beam on the wall and it holds the weight. You don't want it to move. For it to not move, the total weight on the top of the beam has to equal the total weight pushing up from the bottom of the beam and on the ends of the beam. So that's basically a way of thinking about it. Now, in this situation, where we have this beam being loaded like this, the way this beam would fail from stress is a few different ways that are possible, but the most likely and the most reasonable thing that's happening is the cross section of the beam is experiencing compression and tension. So what I'm going to do is I'm going to take a cross section of this guy and I'm going to draw over here. Well, it's not really a cross section, but we're just going to look closer at the center of this beam here. So the center chunk of this beam, let's say we took a slice out of it like a bread loaf and it's at an angle. Pretend it's not an angle. So the center of this beam is essentially not being stressed in terms of compression or tension. That's really what's going to break this. The bottom of the beam, it's like these wood fibers are being pulled apart. And the top of the beam, it's like they're being pushed together. And if you ask why, well, you can imagine that that makes sense because when you load something, if it's supported over here and it deflects, oops, what's that going on here? No, I just want to draw. And it deflects downward like it would bend under the weight, then what's happening is the material on the top of that beam is getting crammed into itself, and the material on the bottom of the beam has to stretch out in order for that shape to change. So we go up here and look at the small bread slice. We know that the top is being compressed, the bottom is being pulled apart in tension. Now, somewhere in the middle, if this is a consistent cross section in terms of same width all the way down, then we know the center is where nothing is happening. So what's going to happen is there's going to be less and less compression as you get closer to the middle, and then you start to switch over and you're going to start to get more and more tension, and that is on both sides. So because this is happening, there's sort of two ways this can fail. Either it's going to fail because of this guy, or it's going to fail because of this guy, because those are the most extreme forces, extreme stresses being placed on the member. So if it fails because of the bottom one, the tension, it's going to be because the wood fibers are literally ripped apart into pieces and they couldn't hold the weight anymore. If it fails because of the top one, it's actually not going to fail because of like the wood fibers being crushed. That's not what's going to happen. What's going to happen is it's going to fail like in buckling. And I'll talk about buckling over here next to it. So forgetting the beam, if I have a column and the column is a vertical member that's holding a bunch of weight. If I have the one drawn there and it's just sitting on the ground, and I have one drawn here that's the same width, and I put the same weight on both of these, you'd ask, well, okay, which one can hold more weight? If it's the same material, same cross-section, one's just taller. Well, it may not be obvious. But what if I were to do this? Continue the ground. What if I had one that was this tall, and I had one that was this tall, and I exaggerated the difference? Same weight on both of them. Can't quite draw high enough here. There we go. But the same weight on both columns. Which one holds more? Well, this might start to, you might start to recognize what's happening here. What's going to happen here is taller, skinnier column is going to fail due to what's called buckling under the weight. It's going to, oh man, pen. It's going to bow outwards and go this way, or whichever way it's going to go, and it's going to fail in a buckling way before it fails under just like the wood's getting compressed and squished. So when it buckles, effectively, we get this weird scenario where this item that's this short, small one right here, that's just being compressed. That's not going to fail under buckling. The wood's not it's not skinny enough. There's no problems. You're just going to crush the wood before anything else, and you're going to put way you can put way more force on the short one because it's not going to buckle, and things buckle faster than just being crushed. So what happens is this buckling scenario is going to fail because what you've essentially done under a buckling scenario is you turned a if I were to just take this whole thing and spin it 90 degrees, if the ground was on the left and my long skinny guy was on the right and he was being loaded like this and he buckles, well, what did I do? Well, I created what's called a moment force on it, and I basically loaded it like a beam almost. So it'd be like I was supported over here and sort of supported over here if it's restrained. And now I have all this weight that's pushing it this way effectively. Even though the weight's really coming in from the right, what's happening once it bends is it's going to act as if all that weight was like instead trying to make it bow down and buckle like a beam. And that's going to make it fail a lot quicker because these things are normally not designed to be beams. They're designed to be columns. So that's why buckling is a problem. Now, that's for a tall, skinny thing. If we apply that premise to a beam, then what happens is the top half of the beam, let me color here, the top half of the beam, come on, is the part that's in compression because of this, right? So this part is in compression. Compression causes buckling. So if the top half of my beam is all in compression, it's like it's all getting pushed in like this, then if I were to look at it from this, like this actual section here, if I were to look at the beam when it's not being loaded, it would be vertical like that. And if it is loaded, what might happen is it might deflect out to the side or it might fail. And what's happening is this top part of the beam is being compressed and it's buckling under the effective like compression force from this guy right here. So that's kind of how one-way beams can fail under stress. Is it's causing either the buckling failure or it's causing a actual tension breaking failure in the bottom of the material because of the tension in the beam right there. So that's kind of a rundown on some sort of stress things. It might be a little heavy, but we're basically concerned with members breaking in one sense. Most of the time, we are actually just going to be concerned with members deflecting too much. So if I have a wall on this side and a wall on this side and a great big beam spanning across, and this is a beam that's creating like a ceiling line to a vaulted ceiling or something wonderful, pretty. And there's going to be a big edge here that everyone's going to see. Well, what I can't have is I can't have this beam be loaded and put a big belly in the bottom of the beam because that's going to be noticeable. If the distance here, let's say it was 1 inch or something, depending on how far that beam will deflect downward, will bend downward, will change if that's acceptable or not. So basically what happens is you load any beam and it's going to deflect some because nothing's perfectly rigid. To be rigid would mean that it doesn't bend. That's just not real. So everything bends some amount. So the stiffer something is, the less it will bend. Excuse me. And the stronger something is, the less it will break. So two different factors. We got to keep both of them in mind, but most of the time we're going to be controlling for this guy, the bendiness, because the bendiness is going to limit most of our beam designs. So that's what's going on. That's how things can fail and break.